Hello and welcome to this talk on chiral helimagnetism and the Hall effect in chromium-3 niobium sulfur 2. So this talk is forming part of the current research in magnetism, this magnetic skyrmions workshop on the 15th of September 2021. And so if you don't know anything about this conference, you are more than welcome to watch this talk. I will also leave a link in the doodly-doo below so you can find more talks like this that will be related to this. And so I'm Daniel Mayo. I'm from the University of Warwick. I am currently a postdoctoral researcher at that institute, and I'm going to be talking about some of the current research that we've been doing. And so first I want to make a few acknowledgements, firstly to Amelia, who has grown all the crystals I'm going to be talking to you today, to Juba, who has been instrumental in helping us understand what has been going on with this system, and to Geeta and Martin, the two project leads at the University of Warwick. And so this research forms part of a bigger research block, this Skyrmion project that is a collaborative research grant between these 5 institutes that are on the right, so Durham University, Cambridge University, Southampton and Oxford. And so today I'm going to give a very brief motivation about what skyrmions are, and why we're interested in these sorts of systems. I'm then going to be talking about the intercalated transition metal dichalcogenides, and then going to tell you about the sample growth. Then I'm going to give a very brief sort of overview of chromium-3 niobium sulfur 2 and show you that it has a very rich magnetic phase diagram. I'm then going to be talking about the Hall effect and the transport phenomenon that we have seen in this particular compound. And so, motivation, skyrmions again. So this is a whole conference on skyrmions, so you're probably very sick of hearing this. But actually, I'm not going to be talking about skyrmions. I'm going to be talking about something slightly different. And so chiral magnets can host unusual phenomena, such as skyrmions, but they can also host other magnetic spin structures, such as these chiral soliton lattices. And well, what are these? Well, magnetic solitons are localized magnetic excitations, and these can be thought of as basically domain walls with 360-degree spin rotations in them. There'll be a nice figure on the next slide, so you'll be able to visualize it there. What's useful to keep in mind is that skyrmions are an example of a magnetic soliton as well, so this is all somewhat related. And so on the left-hand side here, we have the 3 different states that we can have. So in zero field, we can have a chiral helimagnet where we end up with a helix of magnetic spins. As we apply a field, we then get these regions of forced ferromagnetism, and so this is then these 360 domain walls that separate these regions of forced ferromagnetism, and this is really what a chiral soliton lattice is. Then we have a forced ferromagnetic state, so if we increase the field so much that we just push out all of these 360 domain walls, then we just end up with something that looks like a ferromagnetic state. So transition metal dichalcogenides, these have been extensively studied now, so an example would be niobium sulfur 2, tantalum, selenium 2. But when we look at the structure of this, we end up with these layers of niobium and sulfur. We then have quite a large gap from van der Waals bonding in between these different layers. And at this point, we can then intercalate in a magnetic ion. So in our case, we want to intercalate in chromium 3, but there you could potentially intercalate manganese or vanadium or whatever you want, really. The most important ingredient in all of this, however, is that we get a noncentrosymmetric space group. And so by getting this particular stoichiometry, we ensure that we get the noncentrosymmetric space group, as all of these interactions, these chiral soliton lattice, this chiral helimagnetism, is coming from this DMI interaction that we have in our sample. So this has to be noncentrosymmetric. And we're in luck because this does crystallize in the hexagonal noncentrosymmetric space group, the P6322 system. And so how do we prepare these samples? So we prepare a quartz tube, we put in our stoichiometric starting material, so in this case chromium 3, niobium sulfur 2. We also then put in a little bit of iodine. we set up a temperature difference between the two ends of the tube. Our iodine then kicks into action and starts carrying our material around the tube, and we end up with crystals forming at the cold end. And so this is hopefully our chromium 3, niobium sulfur 2 single crystals. And here's a few examples of some vanadium 3, niobium sulfur 2 crystals grown by the same process. You can see these really nice hexagonal shapes. And we found that the best way to determine the phase of these particular crystals is actually to use a transmission electron microscope to easily determine that we do in fact have this a third composition in our sample. So now to take a broader look at what the literature of chromium 3, niobium sulfur 2, and that's what we'll be doing in this slide. So chromium 3, niobium sulfur 2, as you've probably already guessed, is a chiral helimagnet and can stabilize a chiral soliton lattice. And so this is two particular fields that we can have. So in zero field, we'll get our chiral helimagnetic ordering. When we apply a field perpendicular to the helical axis, we'll then get a chiral soliton lattice. But there's also a few other field configurations that we can have. So what happens if we apply the field along the helical axis? What happens if we apply the field at some intermediate between parallel and perpendicular? Well, when we apply the field along the helical axis, we end up pushing our moments towards the helical axis in their chiral magnetic ordering. And so we end up with a chiral conical phase. If we do it at some intermediate position, we end up with a tilted chiral soliton lattice. So basically the moments in our chiral soliton lattice are twisted towards the direction that the magnetic field is pointing. So we still have a tilted soliton, we still have a soliton lattice, but it is just slightly tilted off of axis. And of course, if we apply a sufficiently large field, we can get our forced ferromagnetic state. And so if you're interested in more of the experimental results that are behind this and some of the theory as well, then there's an excellent review that I've listed down here at the bottom in Materials Today that came out last year. And so we talked about the helimagnetism in chromium 3, niobium sulfur 2, so we need to have a quick sanity check that our crystals are in fact what we're expecting. And so we do find the magnetic transition of 111 Kelvin. This is reasonably consistent with the literature. We have seen that there's a chiral soliton lattice in chromium 3, niobium sulfur 2 in our particular samples. And so the chiral soliton lattice is really expected to give an unconventional topological Hall effect. However, nothing's been reported in the literature. There is one report on the Hall effect. They do see an unconventional Hall effect, but they really don't attribute this to being a topological Hall effect. However, hopefully with the data that I'm showing you today, you'll be more convinced that that is indeed the case. And so first, it's worth just looking at the magnetoresistance, as this can be hugely telling about what's going on in these samples. And so what we see is these nice parabolas above the transition going into sort of these sombrero shapes as we get colder and colder. And this gives us a strong indication that we do in fact have some chiral soliton lattice, or at least non-coplanar spin textures in this sample, as this sombrero shape is indicative of spin disorder scattering. So in the chiral soliton lattice phase, we have this quick decrease in the resistivity up until about 2 Tesla, and then once we hit the forced ferromagnetic region, it becomes highly linear up to 9 Tesla, but even beyond that. And so then when we look at the Hall effect, we did see quite an unexpected result. So we saw this giant topological Hall effect, and actually as we plot the maximum of the topological Hall effect as a function of temperature, we see that it indeed flips seemingly at the transition temperature and also decreases with temperature as well, which is one of the hallmarks of a topological Hall effect. What's interesting to note is if we compare this to, say, skyrmion materials such as iron germanium or manganese silicide, the topological Hall effect in these materials is normally on the order of nano-ohm centimeters, whereas we're in micro-ohm centimeters. So this is really quite a substantial difference. And so this presence of a topological Hall effect, it doesn't necessarily mean that we have a chiral soliton lattice, but it is very indicative of non-coplanar spins. But when we take this together with all of the other literature that has observed a chiral soliton lattice, it's fairly easy to draw a line between the two and say that, you know, the chiral soliton lattice is giving rise to this topological Hall effect. However, it was kind of surprising to see this in the orientation that we had. So we were applying the field along the c-axis. So we really should have been applying this along the helical axis. And we should have been really getting a chiral conical phase. And so there's two possible models for what's going on. So when we apply the field along the helical axis, we should have a chiral conical phase. But the chiral conical phase really isn't expected to give rise to a topological Hall effect. However, if we have this second model, so this tilted chiral soliton lattice, then the tilted chiral soliton lattice can indeed give a topological Hall effect. And if we do have a tilted chiral soliton lattice, this would imply that there's an out-of-plane net magnetization, so a planar Hall effect should really be observable in this system. And so this tilted chiral soliton lattice in chromium 3rd niobium sulfur 2 really is nothing new. This has been previously predicted in back in 2017 by Jon Muir et al. And this was from torque magnetometry experiments, but one of the interesting things from their paper is that actually they reckon that the tilted CSL can be stabilized as little as 1.5 degrees off the c-axis. And so if you're really not well aligned, unless you're really well aligned along your c-axis, then it's highly probable that you would stabilize a tilted chiral soliton lattice, which we think is probably the case in the system that we're showing here. And I guess if we go out and look for a planar Hall effect, this can then give us further confirmation that it is indeed a tilted soliton lattice. And so it's worth noting that the planar Hall effect is a little bit different from the conventional Hall effect. So rather than from Lorentz forces in the conventional Hall effect, the planar Hall effect is an interaction between the magnetization and the current in the plane of your sample. And so when we measured this in chromium 3rd niobium sulfur 2, we get these really nice oscillatory 360 oscillations in our rho XX and rho XI. So this is our longitudinal resistivity and our transverse resistivity. The transverse resistivity being the planar Hall effect, the longitudinal resistivity being the angular magnetoresistance. And so these then fit incredibly well to the planar Hall effect and the angular magnetoresistance model, and you can see these dotted lines here fit almost perfectly to the data that we have reported. And so taking this together, the giant topological Hall and the planar Hall effect, what's quite interesting is when you look at the planar Hall effect as a function of temperature, we see that in the low fields, it abruptly turns off at the transition temperature, but also persists at higher fields. And so that we do have an explanation for why this would persist at higher fields, but I'm not going to be talking about it today. But it's really interesting that the low field contribution seems to turn off rapidly at the transition temperature. And so taking both this topological Hall effect and planar Hall effect, we believe this is indicative of a tilted chiral soliton lattice phase in the chromium 3rd niobium sulfur 2. And so thank you for listening. A brief summary is that, hopefully you've seen today that these intercalated TMDCs are quite a rich and interesting family of materials. So really I've only talked about the chromium 3rd niobium sulfur 2, but it's very easy to make other members of this compound, switching out your chromium for another magnetic ion, or switching out your niobium and sulfur for other materials as well. And in chromium 3rd niobium sulfur 2, we have shown the presence of a giant topological Hall and planar Hall effect, and we believe this is indicative of a tilted chiral soliton lattice phase in this material. So thank you for listening, and take care.